Hello, in this video we will begin our discussion of kinetics. In this chapter we have the rate laws, and the next chapter we have the mechanisms. So let's go. So what the heck is chemical kinetics? It's the study of the rates and mechanisms of chemical reactions. Why do some reactions happen faster than others? How do you control this? Either to speed it up or slow it down. And then in the next chapter we talk about mechanisms. How does this reaction actually work? And that gives you information on a fundamental level of what the chemistry is doing. So why is this called kinetics? Well, kinetic means motion. And so you have kinetic energy, which is the energy of something that's moving. Molecules do this. Molecules are moving. The kinetic theory of gases is based almost entirely on how molecules are moving in space. And so that makes sense for rates of reactions, because for a reaction to happen, the molecules actually have to collide, and that involves some sort of motion. And so kinetics makes sense from that standpoint. So the speed or rate of a chemical reaction depends on four things: the concentration of your reacting species, or if you have a gas, this is phrased in the pressure, because all other things being constant, pressure is related to number of moles per area, and that kind of makes sense. And then rate of a chemical reaction depends on temperature as well. You heat it up, it tends to go a lot faster because the molecules are moving faster, and then they collide with more energy, and then they're more likely to collide as well. The physical form of reactants matters too. If you have a solid that you drop into your liquid, you're going to have to wait for the dissolution process to happen in addition to the reaction to happen, so that'll affect the reaction process. And then if you put in a catalyst, it will usually speed your reaction up, sometimes to an amazing degree. And so a catalyst is a substance that you add to a chemical reaction that's not actually reacted overall. So like it's used in the reaction, but it's not destroyed or consumed in the reaction. And it typically makes the rate of the reaction a lot faster. So how do we go about looking at kinetics? So we want to know what the reaction rate is. What is the change in concentration over time? And so one way you could do this is just take little bits out of your reaction at specific times, and then through some method analyze that, maybe a titration, who knows. A way that's really easy is if your substance absorbs light, or like just one of your substances absorbs light, you can measure this, and then through the Beer-Lambert law, we know how to relate absorbance to concentration, and then that makes life really easy. And then you can use a bunch of other methods as well. Honestly, I think absorbance is the easiest one, and then when we do this in Gen Chem, we specifically pick reactions that are colored because it makes it easy to analyze. So the rate of a reaction is analogous to how fast a car is moving. So when we talk about speed, we talk about how far did you go and how long did it take you to get there, distance divided by time. So when we're talking about a reaction, well then we're talking about change in concentration over time. Same idea, how far along its path did the reaction go per some unit time. All right. And so you can plot this, right? Y-axis concentration, x-axis time, and A is your reactant, and your reactant will disappear over time, and then it will form the product. So up in the top left, we have kind of our generic way that we can describe a chemical reaction. And so the capital A and capital B are the reactant and the product, and then the lowercase a and lowercase b are the stoichiometric coefficients. Just kind of a generic way to write a chemical reaction. Not really a big deal, but I figured it'd be worth explaining. So we want to talk about the rate of this chemical reaction. And so the rate relates to the change of the concentration of A and B. So the brackets here mean concentration of. And we use this a lot in chemistry because it's a very convenient shorthand. So square brackets around a chemical formula or a name of something means concentration of whatever's inside those brackets. So when we look up here, rate is equal to the change in the concentration of A divided by time, a change in time, and the same is true for B. Now what's different here is that there's a negative sign hanging out in front of A. So the reason for this is kind of a bookkeeping thing. So when we talk about rates, we talk about a positive rate. Your reaction is going forward from one state to the other, from reactants to products. But when you use delta, that means final minus initial. And so for A, the final minus initial is going to be negative. So we have to put another negative, the one that's circled in red, in front of this in order to cancel out the two negatives, and then our rate is positive again. So any reactant will have a negative sign in front of it when you say rate equals change in concentration over time. So, all right, here's our plot again. And now what this rate is, that changes also as you go through the course of the reaction. Right? So if you're at one point here, your rate is the slope of the line at that point, in effect the tangent of the curve at that point. And then you go to a different point, well now your rate is different. A little farther along the reaction, your rate's even different, so on and so forth. And so we talk about instantaneous rates when we're describing what the rate is at a specific point in time. Usually we'll use initial rates for doing these kind of measurements because that's at least the most reproducible. You mix the stuff together and measure how fast it's going, as soon as you can measure it, basically. And that can be more accurate than waiting some amount of time and then measuring it. So another thing about measuring rates like this, you get more accurate if you have a smaller window over which you're looking. So when you take change in concentration over time, you're going to measure one rate over that time frame. And so if your time is really large, then you're going to get some kind of average of the rates, of the instantaneous rates in that time window. So the smaller delta t, the better. Now, let's kind of keep going with this. So here's our example reaction. We have bromine gas that's dissolved in this liquid with formic acid, and it makes these products. And the nice thing here is the bromine is this reddish-brown color, and as the reaction goes, the bromine turns into bromide, Br-, which is colorless. So what we've been talking about here is the instantaneous rate at any point in this reaction is the change in concentration of bromine with time, divided by change in time. And there's a negative sign in front of it because the bromine's being reacted. Now, again, we can measure the rate of reaction. And we can do this by looking at either the rate of products forming, so how fast are we making products, or you can look at the rate of reactants decreasing. So how fast are we taking away the reactants? Since the reactants turn into products, you can look at either one and it's just fine. They're just different by a negative sign, right? So if we look at this, all right, here's the bromide again. And so for every bromine molecule that reacts, we're going to produce 2 bromide ions. Now, again, we can look at reactants or products. That's fine. And they're going to be off by a negative sign. And then now when we have a coefficient here, well, the bromide ions are produced at twice the rate that you're reacting the bromine, Br2, molecules. Because there's a 2 there, right? For every one of them, you make 2. And so this has to play into our description of the rate of reaction. And so we have our change in bromine with time. It's negative because it's a reactant. And then on the bottom, we have the bromide ion with time down here. And so here we have to add a 2 in order for this to work, right? Because the rate of reaction here and here are going to be the same. So you have to have twice the rate of reaction to talk about the forming of the bromide product, Br-. So what's easier here is instead of having a 2 in front of our rate, is if we just take this 2 and drop it over here. Divide both sides by 2, basically. And then that's what we're doing right down here. So down here we have this factor of 1/2 that's hanging out with the bromide, right? For this rate to be the same for both bromine and bromide, well, you have to have this factor of 2 here. Because this number is 2x twice whatever this number is. So you have to have this 1/2 here in order to cancel that out. So another way to think of this is we define rate, and granted this is kind of an arbitrary definition that we can choose, but we define rate to match 1 mole of the reaction equation as written. So that means you have 1 mole of this, 1 mole of that, 1 mole of that. The 1 there is the rate of reaction. And then anything that has a different stoichiometric coefficient is going 2 times faster than the rate, 3 times faster than the rate, so on and so forth. Kind of the simplest way we can define it, So now we can take these ideas and write the instantaneous rate in terms of all the reactants or products in this reaction. And so here it is, right? The reactants have a negative sign in front of them, right here and right here, because they're reacting away. The products don't have a negative sign in them. Now anything with a stoichiometric coefficient in the reaction gets 1 over that stoichiometric coefficient in the description of rate. And then for all of them, it's just the change in the concentration of that compound with time. All right. So we can talk about this kind of generically, where here we go. We have A plus BB goes to CC and DD. All right. Remember, capital letters are what we're using to represent the compounds themselves. The lowercase letters are the stoichiometric coefficients. And again, reactants negative, stoichiometric coefficients are in fractions. And now if your stoichiometric coefficient comes out to be 1 over 1, just don't write it. But if 1 over 2, you got to write that, you know. So that's how we talk about this. So quick thing to think about, how would you write the rate of reaction for this reaction I give you here in terms of the concentration of NO2? So think about that for a second. All right, here you go, right? It's a reactant, so it gets a negative sign. There's a 2 in front of it, so you get the half. And then it's a change in concentration with time. Okay, now the next step is putting numbers into this. So here's a different reaction, and K2S, potassium sulfide, we're given the rate at which it's reacting at this particular point in time in the reaction. So at that point, what rate is the HCl reacting, and what rate are you forming potassium chloride? All right, so let's rephrase this thing. So this means that the change in the concentration of potassium sulfide with time is 0.035 molar per second. That's a common unit for rate. Actually, I shouldn't say common. That's the unit for rate that we use, concentration per time. Now, this says it's reacting at a rate of 0.035, so that implies there's a negative sign in here somewhere. Your delta K2S, since it's a reactant, is negative, so then we have to have a negative sign here to make the whole world work out. All right. So now the rate of reaction must be positive. We talked about that. And so this 0.035 with its negative sign is this term right here. So then this negative sign makes it positive at the end of the day. Great, so that's what we have. Now, what are we trying to solve for? Is we want to know the rate that the HCl is reacting. So really, you just set this up like a math equation and solve it. And then you find that the HCl is reacting at twice the rate. That makes sense. There's a 2 in front of it. You're using it twice as fast as you would use the K2S. All right. So then now let's look at the KCl. Well, you're forming it here. And again, this is just an equation now. And we know some numbers, and we're trying to solve for this whole mess, the delta KCl over delta T. That's the rate of that particular compound. So you set that up again, the negative sign here, and then you have the negative K2S. This is that with its negative sign, right? And then this negative here goes here. All right. So do that and solve. You get again 0.070 molar per second. And hey, it's producing KCl at twice the rate that it's reacting K2S. And that makes a bunch of sense. So that's what we have for this video. So we're building the foundations of this idea of rates. And then we're going to use this to talk about the rate of a reaction. So now this rate right here is going to change as you go through the course of the reaction. But it's how we describe the reaction. And then keep in mind that's different than what we just talked about, right? This number here is the rate of a particular reagent in the reaction. And granted, if you wanted to know the rate of the overall reaction, you just take this and compute it, and it's equal to that, which is 0.035 molar per second. Okay, that's easy. Anyways, got a little distracted from my closing here. So, okay, given that, we're building the background and foundation we need to talk about rates. So then we'll move on and talk about how we can calculate rates given like a more consistent thing. So it's not just rate at every individual point in the reaction, but we can talk about a reaction overall, and then we'll keep going from there. So keep this in mind, get this on board, and we'll carry on. Thanks a lot.